Alright, this is note card number 6, which is on continuity of a function, and this is going to kind of build on the limits concepts that we've been working on in previous note cards. It also requires that you have some understanding of a lot of different parent functions. So in class we looked at y equals x squared, y equals 1 over x, y equals the square root of x, y equals 1 x to the 1/3 power, and then all the trig functions, ln of x, e to the x. So you want to have some sense of where discontinuities lie in some of those parent functions. So for instance, I'll just do one example here. If we have y equals 1 over x, that equation creates a graph that looks something like this. And there's a vertical asymptote. There's a vertical asymptote at x equals 0. And so you want to just be aware of those sorts of discontinuities in some of these parent functions. Once you have a good sense of that, basically on this right side are the properties of continuity. And so if you have a function that's continuous, like x squared, then if you multiply it by some number, let's say we multiply by 5, then the result is still going to be continuous. That's what this first rule says, is that you can scale any continuous function and it will still be continuous. Now, the second rule says that you can add or subtract two continuous functions and the result will still be continuous. So if we have a function like the sine of x, and we add the function x squared, if both of these are continuous, then this resulting function, let's say it's called g of x, that whole thing will be continuous. That's what that second rule says, and that can be addition or subtraction. The third rule is when you're multiplying two functions. So if we have, and let's take another continuous function like x times the cosine of x. Both of those functions individually are continuous, so when we multiply them together, the result will also be continuous. That's what that third rule says. The fourth one's a little trickier. Essentially, we can have a continuous function, maybe something like x cubed, and if we divide by another continuous function, sometimes it will be continuous, but only if that bottom function, whatever's on the bottom, doesn't have any values of 0, where it equals 0. So one of the only functions that's works for this is if we had e to the x on the bottom, and that's because e to the x looks like this, and e to the x never equals 0. You could also have some situations like if you had x squared plus 1, that would also work because x squared plus 1 is a parabola that's above the x-axis, and so it doesn't have any values where you're going to get it divided by 0. So the quotient one is a little trickier, but that's basically what's going on there. You can divide a continuous function by another continuous function as long as that bottom function doesn't have any values where the y value is 0. And then lastly, number 5 says if f and g are continuous, then f of g of x is continuous. So for instance, if we had the cosine of e to the x, the cosine is a continuous function and e to the x is a continuous function, so when we get some kind of composite like this, this resulting function will be continuous. That would also work if we had something like e to the cosine of x. So that's what that last rule is saying. Alright, moving on to some of the problems. Let's look at the first one. Now this is a piecewise function, and so when you see piecewise functions, you're going to use these rules over here. It says, using h below, for what values of x is h not continuous? Justify. Now, this piecewise function has three separate pieces, and each of those pieces on their own are continuous. Negative 2x plus 3 is continuous, that's a line. 3 is continuous, that's just a horizontal line at y equals 3. And x cubed minus 6x plus 3 is a continuous function, that's a cubic function. So each of these pieces on their own are continuous. Now we have to use these rules to see whether those pieces match up. And this is where limits are going to come into the picture. So this is our checklist essentially for checking for continuity. We always want to go through this checklist, and if any of these three things are not true, then the function is not continuous. All three of these have to be true in order for a function to be continuous. So number 1 says f of c is defined. So let's look down at our function here. Is f of negative 2 defined? And the reason we're looking at negative 2 is where these three pieces come together. And so it's the only place where we could have a discontinuity. We know that that first piece is coming in with a negative slope and it's a line. We know the second piece is just a point, and that point could be here. That point could match up with our line. So we're just not sure where that point is. But if there's going to be a discontinuity, it's going to be at negative 2, because that's where all the pieces are coming together. So first thing, is the function defined at negative 2? It is. The value is 3. So we would say f of negative 2 equals 3. The second thing on our list says, does the limit as x approaches, and again, c in this case is negative 2. So the limit as x approaches negative 2, does that exist? Well, it exists if the limit from the left-hand side and the right-hand side are the same. So if we plug negative 2 into the top equation, we get 7. And if we plug negative 2 into the bottom equation, we get negative 8 plus 12, which is 4, plus 3, which is 7. So we get 7 from the left-hand side and 7 from the right-hand side. So yes, the limit as x approaches negative 2 for h of x equals 7. Now, we've got the function is defined at negative 2. The limit exists at negative 2. Now we have to check whether those are the same. And you can see that one of those things is 3 and one of those things is 7. So those are not the same. And so we can say no, because f of negative 2 is not equal, and it's not f, it's h of negative 2. H of negative 2 is not equal to the limit as x approaches negative 2 of h of x. And basically what that looks like is we've got some function where we're approaching 7 from the left, we're approaching 7 from the right, but the point at negative 2 is not 7, it's 3. So this picture is not continuous. Alright, so that's number 1. And this is how you want to justify it. This is a good way to justify it. Number 2, if the function f is continuous, and if f of x equals x squared minus 4 over x plus 2 when x is not equal to negative 2, then f of negative 2 equals something. So essentially, we have a function here where, and if you remember back to limits, if we're going to look for the limit as x approaches negative 2 here, we would factor and cancel. So we'd have x plus 2 on the top times x minus 2 over x plus 2. And so what's going on here is we've basically got a line with a hole in it at negative 2. And so it might look something like this. Like that, and then we've got a hole, and it continues down that way. Now, the function f is not defined by this equation at x equals negative 2. What they're asking us to do is define it at negative 2 in such a way that makes it continuous. So essentially we need to find the place where that hole is and define f of negative 2 at that y value. And the way you do that is you just plug negative 2 into what's left up here. So if we plug negative 2 into x minus 2, we get negative 2 minus 2, which is negative 4. And so that's the y value that will make this continuous. And so the answer here is negative 4. Number 3, which of the following functions are continuous for all real numbers? Well, this one is continuous. The tangent is not continuous. And x to the 2/3, this one is continuous as well. One way that you can think of that is x to the 1/3 is continuous. And x to the 2/3 is just x to the 1/3 times x to the 1/3. So by the rule, the product continuity rule, since these are both continuous functions, the result is a continuous function. And so 1 and 2 are continuous. So the answer is D. Number 4, for what values of the constant c is the function g continuous over all reals? So here we've essentially got some line here, which is continuous because lines are continuous. And we've got some parabola, which is continuous because quadratics are continuous. Now they meet up at 3. At x equals 3. So if there's going to be a discontinuity, it's going to be at x equals 3. So what we want to do is we want to set those equal to each other because we want them to be the same. We want them to have the same y value so that they meet up. And if the picture helps you here, we have some situation where we've got a line coming in here and then some parabola. And there's going to be some c value. As we change the value of c, the locations of that line and that parabola are going to change a little bit. And there's going to be some c value where the y value at, let's say that this is x equals 3. The y value at x equals 3 for the parabola and the y value at x equals 3 for the line are going to be the same. So the way that we algebraically do that is by setting the equations equal to each other. So I'm going to say cx plus 1 equals cx squared minus 1. And the x value where we were trying to get them to meet up is 3. So that becomes 3c plus 1 equals 9c minus 1. And if we just go through the algebra and solve for c, we'll get 2 equals 6c, which means that c equals 1/3. And that's the answer. C equals 1/3. That's the note card on continuity. Make sure to play around on Desmos with this last example so that you can get a better visual for that. And if you just add the letter C, it'll create a slider for you so you can kind of play around with that and make sure that you see what's happening there and why C equals 1/3 gives you a continuous function.